Should be good? Okay, very good. So we have the second matrix model of this block by Harish.
Okay. All right. So this is I'm going to talk about heavy operators in matrix models and their universality. So this is some work with Andrea and Pedro, both of whom are in the audience. It should be out next week. Okay. So let me. Oops. Okay. So okay. Let me just start with some motivation about what we're trying to do. So in ADS-CFT, when you insert a heavy operator in the CFT whose dimension scales with n squared, it's so heavy that it back reacts and it changes the bulk geometry. That's the usual lore. And n here, I'm assuming I have some large n gauge theory. Okay. Now, if the heavy operator that you're inserting is some typical high energy operator, then we expect it to be dual to a black hole in the bulk, because typical high energy states are thermal, and thermal states are expected to be dual to black holes in the bulk. Okay. Sorry, what's okay, let me try to. How does it work? View. Okay. Okay. Oops. So the expectation value. Okay. And now you put a heavy operator, and you now ask what are the expectation values of probes in this background. And if it's dual to a black hole, it should only care about some coarse-grained features. It shouldn't depend on the details of the operator. So we would like to see something like this explicitly in the CFT, but we don't know how to do calculations in the presence of heavy operators at strong coupling, even in nice theories like n equals 4 superangles. So if you assume that you have some BPS operators, you can make progress, but for generic heavy operators, we don't know how to do this. So we turn to matrix models. So in John's talk yesterday, he argued that polarized IKKT is a promising model for something like this. And it has this nice 10D gravity dual. But this is still too complicated for what we are interested in. So what we do is we drop all fermions, and then we just go to D equals 2. So D is like the number of bosonic matrices here. So it's a Hermitian two matrix model. And that's what I'm going to consider now. So this is still a Yang-Mills type model. So I have a commutator squared term here. And then I have mass terms, x squared by 2 plus y squared by 2. So that's the, so okay. And this is called the Hoppe model. It was solved by Hoppe in this paper in 89, also studied by these people in a paper in 98. Okay, so this was solved at large n and at any coupling lambda. But the thing is, it's not a simple solution. It's an implicit form. It has some elliptic functions. So it's not very nice to work with, but we're only interested in the strong coupling limit, because we expect that holography is something that happens at strong coupling. So, and things simplify a lot when you go to lambda much bigger than 1. Okay, so let's look at how that works. So in this paper by these authors, they solved this model at strong coupling, and I'm just going to review that result. So what you do first is you take the Hoppe model and you diagonalize one matrix. So that's so I diagonalized x, and little xi are the eigenvalues of x, and then u is the unitary that diagonalizes it. Okay, and then we get the usual Vandermonde matrix, Vandermonde term. Yeah. Okay. The rest of it is just straightforward. And now what you can do is integrate out y, because it's a Gaussian integral in y. Stop me if there are questions, by the way. Yeah, when you integrate out y, you get this factor. The numerator is just the Vandermonde from before. The denominator is what you get from this part. Okay. Now at large n, we can just do saddle points. So you have some large n integral, and this is just the saddle point equations for the n eigenvalues. And now you can go to the continuum limit. So what I mean by that is I have n eigenvalues, and I assume they all form a continuum, and rho is the density of these n eigenvalues. And we can try to solve this now at large n. Okay.
So, sorry, what is U decouple?
What decouple, sir? Yeah, I should mention that, because nothing depends on u here, right?
Why did that happen? Because your product said X is on Y, right?
So okay, so I diagonalized u, right? So in the integrand, I just have x, u dagger, u. And I can absorb the u into y.
Oh,
So, yeah. Okay. So now as I said, you want to solve the previous saddle point equation at strong coupling. The nice thing that happens at strong coupling is that this integral that was in the last slide is somewhat nice. So notice that this looks like a Lorentzian. This is almost a Lorentzian, 1 over 1 plus lambda x squared, where lambda goes to infinity. But then you have this extra piece of 1 over x minus y. So it turns out that this kernel is just the derivative of a delta function, not a delta function. So at strong coupling, what you get is integral delta prime times rho, which gives me rho prime. And then you have 1 over lambda corrections. Okay? So now we can plug this into the saddle point equation, and what you see is rho prime is linear in x. So let me just go back 1 second. So I just showed that this is rho prime, and then I have that equal to x. Okay. Oops. Okay. So that's rho prime is proportional to x, which means when you integrate rho, you get a parabola, right? So you get something quadratic in x, which means the density is a parabolic density. And that's what I wrote here. And you can get the precise shape of the size of the parabola. So L turns out to be something like this. Okay, so what happens at strong coupling is that is the size of the parabola is very, very small. So it goes like lambda to the minus 1 over 6. So it's almost a delta function support for the density, but you have some width. Okay. Now let's just verify that this was the correct analysis. So this is just some trivial check, which is I solved the discrete saddle point equations at some large value of n and some large value of the coupling. So I have to go to very high lambda, essentially because the expansion goes in powers of lambda to the minus 1/6. So I took 10 to the 4, but then you also need to ensure that you're in the 't Hooft limit, which means n should be big. So I have to do n equals 600. But okay, you do that, and then you get a bunch of solutions for this. So it's some big polynomial equation essentially. And in these blue dots are roots of that equation, and then and the density of the roots of that equation, sorry. And then that matches very nicely with the dashed red line, which is the parabolic density that we derived. Okay. So the parabola is correct. Now let's see what, okay. Now what we're interested in is now to go to put heavy operators inside this integral. And I'm going to make a simplifying assumption that the heavy operator depends only on x. The reason is that I can still integrate out the y and then get saddle point equations for the x's, for the eigenvalues of x that way. Okay. So I'm going to consider these sorts of operators. The first one, the simplest, is I can just put an operator in quotes because I'm doing e to the power trace v of x, so it's like a potential. And v of x is some polynomial potential. It's a single trace polynomial potential that I'm inserting. So that could be a deformation of the integral. And you could also put classical sources for x. So that's trace j times x, and j is some external Hermitian matrix. Okay, and you could also do characters, which is the last class. These are basically polynomials of eigenvalues of x. And they're labeled by some un Young tableau R. And it's a nice basis because it's orthogonal in the Gaussian measure. But okay, we don't really need to worry about what it is, except that it spans all invariants of a single matrix. Okay, now what we want to do is consider all of these in turn and see what happens when you insert them into the Hoppe model at strong coupling. Let's look at the first one, which is the potential, so e to the minus trace v of x. And then you can again do the saddle point equations. And I get rho prime again because I still have the delta prime kernel, and that just is equal to v prime now. Okay, so if you are at a generic position x, then the right hand side is huge, right? Because I have lambda here. But we know that rho of x should be a normalized density. So the only way that can happen is if the support of the density is very close to zeros of v prime. Okay, so let's then expand v prime around one such zero. So x star is 0 of v prime, and then we can Taylor expand, and you get v double prime times x minus x star plus dot dot dot, right? So now once again we end up with something that is basically a parabola, because rho prime is linear in x, and rho is now a parabola. It's centered at x star, is the 0 of v prime, and it has some renormalized size. Okay. Any questions about that? Okay. If not, let me keep going. Yeah, so more generally, you can have many solutions of v prime of x equal to 0. So you can have many roots. And you can have multi-cut solutions, which are many parabolas centered at the zeros of the potential. And then you can determine the sizes if you tell me what the filling fractions are, which is how many eigenvalues sit in each of these cuts. And now I just did some numerics for, once again, with these eigenvalue numerics. I take a double well potential, which is what I have in red here. Okay. And I have a two-cut solution with which are centered at the minimum of the potential. And again, the analytics and the numerics agree. The numerics are the blue dots and the analytics are the red dashed lines. Okay.
Is there any qualitative difference from the one matrix model?
Yeah, because we don't have van der Waals, right? We have some generalized van der Waals term.
But I mean, that's also what you would get in the one matrix model, right? Some approximate semicircle neighborhood.
Oh, but then it wouldn't, if you take these minima close to each other, they'll start to merge together, right? That's not something that would happen here. Because you have very strong coupling, these supports are very tiny. So if the potential does not scale with lambda.
So you say the distribution is narrower.
Yeah, exactly, yeah. It's really universal. If you do one matrix model, you get non-trivial shapes, right? It's not going to be exactly a semicircle. Right? Okay. Now let's put the next class of operators, which is these classical sources. So which is, I'm going to insert e to the n trace j dot x, and j is some Hermitian matrix, as I said. Now let's go back to the Hoppe model, and now this time the unitary integral you cannot integrate out anymore because it couples this way. So you have j u x u dagger, and j is some external matrix, so you can't absorb it into that. It makes no sense. Okay, so we have to deal with these unitary integrals. Now the nice thing is that there's a lot known about this particular sort of unitary integral. So that it's called the Harish Zubair integral, HCIZ integral, which is given by this. So notice that this is precisely of the same form. J u x u dagger. This is A and B are two external matrices, and you're integrating u and u dagger. Okay, and we know what the result is even at finite n. So this is given by some simple determinant formula. So little a and b are the eigenvalues of the matrices A and B, capital A and B. So I have a n by n determinant here of ai bj, and then you have some trivial van der Waals factors in the denominator. Okay, so I'm going to go a bit fast over this point, but how long do I have? Yeah, so what we want to do is take this HCIZ integral and take the large n limit. Notice that it's not easy to do something like that because n by n determinants are hard to compute. But there's also another nice result by Matthijssen, who basically showed that the large n limit of the HCIZ integral is given by a one-dimensional fluid flow. So this fluid is basically, you should think of it as the condensation of the eigenvalues. So at time t equals 0, the fluid has a density given by density of eigenvalues of A. At t equals 1, the fluid has a eigenvalue density B. The density of the fluid is eigenvalue density of B. And in between, it satisfies some simple differential equation. It's called the Hopf equation. So I package F is equal to V plus I pi rho. V is the velocity of the fluid, rho is the density of the fluid, and then it satisfies this equation. Okay. A simpler, more undergrad way of thinking is this. This is just the 1D Navier-Stokes equations with some particular equation of state. Okay, so now what we need to do is to find the value of log of the HCIZ integral, you need to solve for this fluid flow with these boundary conditions. And then you look at the action of this fluid, and that gives you the result you want directly at large n. Okay, so now what you can do is plug this into the integral we're interested in, and then do some, you need to also vary with respect to the density of x. And when you do that, basically you get some saddle point equation for x, which looks like this. Yeah, I just wrote it down to say that you can do this explicitly. but essentially you get some relation between the velocity at the initial condition and the density at the initial condition, so it's some sort of a gluing condition. And now what you need to do is solve this boundary condition with the fluid equations. That's still non-trivial to do, but there is one more nice feature, which is that this fluid is integrable. So you have an infinite number of conserved charges, and then using those, what you can show is the moments of these two densities are related to each other. Maybe that was a bit too fast, but all I want to say is that there is a procedure with which you can relate at the end of the day moments of your source to the density of x. So you do that, and what you do in the end, what you get in the end is that the density is still given by a parabola, and the center of the distribution of the parabola is trace j. So it's the center of mass of your source j is the same as center of mass of the parabola. And then the support of the parabola is something like this. Okay, so this is basically the same as the same factor that we found before with 1 over lambda to the 1/6. And you have this extra new factor, which depends on the source. Notice that this can actually vanish. So which means that when you change j, more precisely when you increase the variance of j, then at some point when the variance of j becomes equal to 1, you hit a singularity, so the length blows up, and then you have a phase transition. Below, when the variance of j is less than 1, you have parabolas. After that, it's some non-universal distribution. So that's a nice result. Now let's look at a particular example. I take j to be uniformly distributed on this interval minus alpha by 2 to alpha by 2, where alpha is some parameter. And plugging it into the previous formula, you see that you should get a parabola centered at the origin, and L of alpha is given by this. So I just plugged it in. Now there's a critical value of alpha, which is 3.464. Okay. Now let's do numerics to confirm that this is what's happening. So it's again the same eigenvalue numerics that I showed before. Okay, so this first row is for alpha less than the critical value, where we expect parabolas. And notice that these are not the same parabola, of course. As you increase alpha, the size changes. It's actually increasing, so 0.3, 0.6, so it's an increasing parabola. But on the right, what I do is I normalize all these densities such that they have unit variance. And once you do that, they all collapse to the same curve. Okay? And in the bottom row, I have, after the phase transition, I don't have analytic predictions, so these dashed lines were actually analytic predictions. For the bottom row, I don't have analytic predictions, but you can still do numerics, and they give you some curves, and they don't collapse to anything nice, of course. Okay, so that's one example. Any questions about that?
So it's not a Gauss-Witten transition.
It's on the right.
Can you say something about the nature of the transition? I mean, it's not like a Gross-Witten-Wadia transition. It's
So
totally
that's
other.
in some. It's a unitary matrix. I'm not sure.
I mean, where the eigenvalue distribution changes topology.
Right. Yeah. Here it's still. Yeah. It's still some finite support. It's just not a universal distribution.
And I mean, so there's some critical exponents.
There could be. Yeah. We didn't analyze that. I think that would
Looked
be
like you
very
had a
nice to see.
1/3 on the previous slide,
The 1/6
or 1/7.
is already in this phase. It's about how this size scales with lambda.
Sorry, can you go back one slide? I guess that 1/3.
This
there
1/3.
is- What is L again?
Okay. Yeah. You're right. Yeah. Sorry. Yeah. L of alpha has that critical exponent. in it.
What is L again?
Oh, it's the size of the parabola.
Okay, I see. Oh, but then it's blowing up.
It's blowing up. Yeah. Yeah.
I see.
Yeah. Okay, so now let's go to the next case, which is characters. I'm going to be very schematic here, but basically you can again show at the end of the day that you get a parabola. So we don't need to know too much details, but essentially I again use this integrable fluids. And okay, so when you have a Young tableau R with order n squared boxes, that's what I call a heavy operator. In that case, you can define some little HIs, which is some algorithm. Basically, you take the number of boxes in the ith row plus n minus I. So these are called the shifted highest weights. And the parabola parameters are given by some moments of h. So the center of the parabola is this, and then L is again something like that. And once again, we have this 1/3 factor. Yeah, okay, and there's also some critical phenomena here when H is of some sort, but okay, it's, let me not go into the details. But the main takeaway is that you still get parabolas for characters. Okay, all right, so now we've been studying densities of eigenvalues of X, which means if you know the density, you can tell me what are all moments of X. So if I put a probe like trace X to the n, if you know rho of X, you can tell me what that is. But what if there are both X's and Y's, right? For instance, if you want to evaluate something like this, I have a bunch of X's, a bunch of Y's, and then I put a huge operator. Are they still universal? Is there some nice description for these? Okay. So what you can do is, because the y integral is Gaussian, so sorry, here I'm still doing O huge of X only. So because the y integral is Gaussian, you can do just Wick contractions, right? And by doing that, you can reduce everything to something about the X's that involves only the X's. And you know the density of X, so you can evaluate that. For instance, if you do it for trace commutator squared, you can show that it's equal to -1/2 lambda. It scales as -1/lambda. This is for the vacuum, but if you put a huge operator, you still get something like this, but that scales as 1/lambda. Okay, and then you can look at the ratio of these two things, so which is trace commutator squared over trace X squared, trace Y squared. If this is small, that means that the two matrices commute with each other, right? So there are two ways that the commutator squared can be small. Either the matrices are small or the matrices commute. Now, by looking at this ratio, I ensure that the matrices do commute because this is small. It's not that the matrices go to 0. So therefore, you can, because the matrices commute, you can define a joint density of eigenvalues of the two matrices. And in fact, when the density of X is a parabola, you can show that the joint density is it's an ellipsoid. So up to some normalization, it's square root of 1 minus x squared over Lx squared minus y squared over Ly squared. And Ly, which is the support in the y direction, is related to Lx in some simple way. Okay. So now once you know this joint density, you can find all moments, all mixed moments, because now firstly the matrices commute with each other, so you can put all the x's together, all the y's together. So it's integral rho times x to the power sigma ai, sigma bi. Okay, so we have a prediction for basically all leading order moments involving all matrices. Sure.
So this quantity rho only means something at infinite lambda.
That's right, yeah.
So can you give it some meaning away from there?
Well, you could, in principle, define some joint density for eigenvalues, but we wouldn't know how to.
Right. Okay, there's still a joint density for the eigenvalue.
Yeah.
I see, but this relation isn't true.
This relation isn't true.
Okay,
Yeah.
okay, I see. Yeah.
Okay. All right. So now let's look at now more general things, which is let's move away from heavy operators of x. Let's put heavy operators of x and y. For instance, one simple example is I put a classical source for x and a classical source for y. But now the y integral is no longer Gaussian. If you integrate it out, you get, okay, it's still Gaussian, but when you integrate it out, you get some crazy things involving jy. So we wouldn't know how to make progress. So what we did is we used hybrid Monte Carlo to study these cases. So this paper was very nice where we learned how to do this thing. Okay, so as I said, we don't have analytic predictions, but if the distributions are parabolas, which as we will see they still are, then we can find their support by just measuring the moments in Monte Carlo. So for instance, the moment of x squared will tell me what is Lx squared. Yeah, okay. So here, if this was a parabola, trace x squared is Lx squared over phi, trace y squared is Ly squared over phi. So that's how we estimate the sizes of the parabolas in the plots next. Okay, so here I'm going to take a particular case, which is Jx, the source for x. I just take it to be some diagonal matrix, which of course I can always do. And Jy I take to be some, it's some general matrix. Now I take the eigenvalues of Jx and Jy to be uniformly distributed on a rectangular strip. Okay, so that's this rectangle in red here. and U is going to be just it's a random unitary. Okay, so when you do that, of course, as I said, we don't know how to do this analytically, but this histogram is what I get from Monte Carlo. The yellow histogram is the density of y, and the blue one is the density of x. And then we can take these histograms, compute the moments of x and y in these histograms, and get Lx and Ly, and they match perfectly. As you can see, these solid lines are parabolas that you get from what I just said, and they match with the histograms. Okay, so that's the 1D density. And here I show the 2D density, which is x and y simultaneously, right? I can look at the density of x and y, and then that's the histogram, the 2D histogram I've shown. And this red dome is actually the ellipsoid distribution. So that also agrees pretty well. So okay, it doesn't matter that we put heavy operators for both x and y. They still are in the same sort of universality. Okay, this we can just ignore. I just wanted to show the source here. Okay, any questions about Monte Carlo, stuff like that?
You have 2 minutes.
Okay. Ooh, okay. Okay, let me just speed up a little bit. Okay, this is just another example just to show that you have phase transitions. So I have a ring here. So I put sources on a ring of one radius and sources of a ring on another radius. Okay, you can ignore most of the right-hand side, but basically there's a phase transition. Before phase transition, I have a parabola. After phase transition, it's some crazy non-universal distribution, just as we saw in the 1D case. Okay, so yeah, actually I didn't have to rush because I'm done. So all right, so what have we seen? We saw that for a large class of heavy operators in the Hoppe model, we have universality of probes, and in fact, once you measure some simple probes, like earlier we saw if you measure trace x squared and trace y squared, but in general you could have these ellipsoids in some, they could be shifted, they could be at some orientation. So once you measure these 5 moments, you completely determine all leading order probes. That's the claim. And now, okay, so there's also some nice phase transitions when you go from the universal to non-universal phase. And it would be nice to look at the vicinity of these critical points, maybe some double scaling. It would be interesting. Okay, so one question is, does this universality we found, does it persist for holographic models, like the polarized JKKT of Joao, the lower dimensional supersymmetric versions that Adrian discussed? We could study those at strong coupling and see what happens. But of course, it's not easy to do that. You could use localization, but that doesn't tell you about general probes. Yeah, in particular, this d equals 4 model where there's no sign problem, it could be very useful because you could do Monte Carlo. Okay. Yeah, so another thing is that I only told you how to evaluate correlators of the form trace, a single trace operator. So that's a disk topology in large N counting, but you could also ask how do I evaluate connected multi-trace correlators, which could be more relevant for, for string theory in the sense that those are supposed to be string amplitudes with some higher genus and so on. Yeah, so I think that's all. Yeah, that's all. Thank you.
So is it true that the phase transition you discovered only happens in the observables where you explicitly break the SUN invariance, where you have you add a matrix J?
Oh, no. It also happened for the, I rushed over it a little bit, but here, for instance.
It also happened for the characters?
It also happened, for characters, no, that also, characters of a single matrix, you also have phase transitions there.
Okay.
Yeah, but also when you have sources for x and y, for instance, as I do here. So I put jx and jy eigenvalues along this red ring versus along this blue ring.
No, but
So
there you're adding a background field that's
Yes.
that's a n by n matrix, right?
That's an
And
n by n
coupling.
matrix.
So that's what I mean by explicitly breaking the UN.
Ah,
invariance.
you're right. Yeah. Okay. So, but you can do it for characters, and it also happens there.
So I ask because that's something that I guess makes us uncomfortable in like in a gauge theory, right? It's like explicitly breaking the gauge invariance.
Well, actually, sorry, are we breaking UN because I still integrate over a unitary, right?
You don't integrate over J though, right?
I don't integrate over J.
J
But
is
the
some-
eigenvalues are going to be, the eigenvalues of X are going to be UN invariant still. Or the matrix X is going to be UN invariant. Right, because I'm going to integrate over U.
If you introduce like a source, which is some n by n matrix J, and couple it by products to your matrices, then the overall rotation, overall basis transform, you're fixing a basis, is what I'm saying, right?
Yes, okay, yeah, I see what you mean, yeah.
Yeah,
Yep.
but sorry, I asked partly because, so if I remember correctly, the like half BPS correlators of these enormous operators in supersymmetric theories
Mhm.
localized to some similar matrix model, is that right? And
They
some-
actually localize to the Hoppe with zero coupling.
Oh, okay, okay.
And there's no universality there because we know that the bulk dual is LLM, which is described by a black and white coloring of the plane. So there's many geometries which depend sensitively on the half BPS operator you insert.
So that's not quite as interesting as what you studied yourself.
Yeah, because there are no black holes in the half BPS sector. So yeah.
Any other questions?
You go back to the final slide and digest your future.
Oops. Yeah.
Not yet. Well, maybe you can make some comments in higher dimension.
Yeah, I had a slide for that, but I did not have time. Yeah, okay. So if the moderators allow me, let me just show a couple slides. So one nice higher dimensional generalization is this three matrix model. The nice feature about this is notice that if you integrate out the matrix Z, so Z is Gaussian, when you integrate it out, it gives you back Hoppe for X and Y. So what's happening here is you have some Myers term, ZXY. So it's SO3 invariant. So you can actually uplift all the results that we had for the two matrix model to this three matrix model. For instance, you can now define a joint distribution for X, Y, and Z. And that turns out to be, for the vacuum, that turns out to be uniform inside a ball. Okay, and now you could also start asking what happens if I insert a huge operator inside this three matrix model, and you can also make progress there. Okay, so it's going to be some squashed ball instead of a ball. So that's one generalization to higher dimensions, but you could also ask, what about these more simpler Yang-Mills type matrix models, right? So I have bosonic Yang-Mills model with a mass term and just commutator squared for all pairs X, mu and nu. Now this model is actually quite different in d bigger than 2 as opposed to d equals 2. For instance, when you go to strong coupling, you can completely drop the mass term. You can't do that for the d equals 2 model. It's important to have the mass term. And another thing is the matrices no longer commute at strong coupling. Okay, so, and you still have universality as you pointed out to us, but it's not as rich as the Hoppe model. So what you have is the only modulus is the center of mass of the distribution. It's going to be, you won't have, we think there are no interesting phase transitions. You just get some blob somewhere depending on the source you put. Yeah.
So the universality you're referring to is the statement that even if the potential is not exactly quadratic, the distribution near the minimum is exactly a parabola, or
It's strong coupling, it's exactly a parabola. Yeah.
Okay, I see. So it's really it's like even more universal than the Wigner semicircle.
Oh yeah,
It's somehow like
Yeah,
more robust
that's
because
right,
of the contribution of the y integral.
Yeah, but you don't even have to do potentials, right? For instance, the sources I put, they're not some single trace nice potentials. There's some complicated objects, and that still preserves this universality.
Yeah, so in d greater than 2, that's where, I guess that's one of your points in the discussion, right? That's where the fermions play a role, because this model
That's right.
is very non-commutative, right? If you go to strong coupling, the matrix is just clumped, they just get smaller for the lambda minus one core. But
Right.
if you have supersymmetry, then they don't.
They want to.
They want to still be more commutative, at least in the limit. So maybe that's an important property to get some supergravities. But
Right.
all models of that Adrian showed have this property. So probably that's not sufficient. Maybe it's necessary. I don't know.
Right.
Let's thank Harish. And now we have a longer coffee break, and so we start again either here or upstairs at 11:45.